A single point of penetration initiated a rapid, catastrophic chain of events. The blast tore open the forward hull and drove violent shock through the cargo spaces. Highly volatile aviation gasoline escaped containment, and its vapors mixed with air inside the damaged compartments. Moments later, those fumes ignited, transforming the forward atmosphere into a localized inferno. The resulting fire and flooding drove the ship toward the loss of stability that would end in complete inversion. This sequence of explosive destruction and complete inversion claimed the United States ship Mississinewa. The loss of the fleet replenishment oiler required a precise alignment of destructive physics, resulting in the deaths of 63 American sailors and 1 Japanese pilot. On November 20, 1944, the ship sat anchored in the deep lagoon of Ulithi Atoll. As a massive auxiliary oiler, the vessel functioned as a floating strategic reserve. The hull contained thousands of tons of cargo, refined aviation gasoline, diesel fuel, and a far larger load of heavy naval fuel oil. The ship was heavily laden, with its center of gravity carefully managed by the distribution of its liquid payload. This stability was violently erased by an Imperial Japanese Navy-manned suicide torpedo. The weapon, known as a Kaiten, was essentially a modified heavy torpedo piloted by a human operator, allowing for precise terminal targeting. The Kaiten struck the starboard bow of the oiler. The torpedo warhead detonated against the exterior steel plating. The primary explosion sheared through the half-inch steel skin, obliterating the immediate framing and rupturing the forward containment bulkheads. The sheer force of the blast created a massive void in the starboard section, inviting immediate asymmetric flooding. Ocean water rushed into the torn compartments, pulling the bow down and helping drive the ship toward the fatal port roll, described by survivors and later wreck investigators. The kinetic damage opened the way for the cargo reaction. Ruptured aviation gas tanks released fuel into the damaged forward spaces, where the mixture was ready to ignite. A massive secondary explosion ripped through the forward section of the ship. An uncontrollable, superheated fire engulfed the forward third of the vessel. The intense thermal load began to degrade the remaining steel bulkheads. As the fire raged, the structural strength rapidly collapsed. The intense heat eventually reached a magazine aft, triggering another fatal detonation. The additional blast compounded the flooding, fire damage, and structural failure already consuming the ship. The stability failure now became mathematical. Flooding, firefighting water, fire damage, and shifting liquid cargo moved the ship beyond the point where its center of gravity and center of buoyancy could generate a useful righting force. The righting arm collapsed. The wreck's final posture was fixed by flooding, structural damage, and the dead weight of the compromised hull. The geometry of the final resting place defined the entire future of the wreck. The seafloor of the lagoon was located at a depth of 130 feet. The massive, top-heavy structures of the inverted ship, including the bridge deckhouse and the heavy cargo masts, smashed violently into the thick silt of the seabed. These structures acted as a foundation, absorbing the impact and burying themselves deep into the mud. Above the crushed superstructure, the exposed bottom plating formed a broad, workable steel platform. Broad, accessible areas of the inverted hull formed a workable steel platform above the crushed and buried superstructure. The accessible inverted hull gave the divers working depths ranging roughly from 80 to 112 feet, with much of the operation centered near 90 feet. Inside the overturned cargo tanks, lighter fuel remained trapped beneath steel tank tops, held there by buoyancy and surrounding water pressure. The violence concluded. The ship settled in the dark, a silent tomb locking thousands of tons of cargo inside a decaying steel envelope. An estimated 18 to 24,000 gallons of heavy black fuel oil leaked from the wreck over roughly 2 months, staining the waters of the Pacific atoll. This release turned a long-known shipwreck into an active threat to the reef and the subsistence fishing ground above it. The wreck was familiar to local inhabitants and visiting divers, but the scale of the threat remained hidden inside the inverted hull. The delicate physical equilibrium finally failed in the summer of 2001. A tropical storm had recently passed through the area, and investigators treated it as a likely contributing factor rather than a proven single cause. Whatever the exact trigger, oil began bleeding from weakened fittings and damaged areas into the surrounding reef system. The root cause of the renewed danger was the slow chemistry of a steel wreck in warm salt water. Corrosion began the moment the ship went under. and after 57 years, it attacked plating, seams, valves, fittings, and damaged areas unevenly. Some hull measurements still appeared surprisingly sound for the wreck's age, but localized corrosion and old battle damage created weak points where oil could escape. At the same time, the trapped oil pressed upward against tank tops, seams, valves, and fittings. The vessel was no longer a working naval structure. It was a damaged, aging wreck holding a large volume of oil in places never designed to serve as permanent underwater containment. The barrier separating that cargo from the lagoon was uncertain, localized, and deteriorating. The danger was not total failure at once, but one weak point, opening enough to restart a damaging release. The release triggered an immediate environmental emergency. The United States Navy deployed a specialized mobile diving and salvage unit to execute an emergency triage operation. In early 2002, military salvage engineers arrived on site to stop the active bleeding. Their immediate objective was strict mitigation and stabilization. They had to secure the compromised sections before the entire hull suffered a catastrophic collapse. The diving teams meticulously surveyed the vast, dark expanse of the corroded steel plate. They confirmed active leak points across compromised tank areas and fittings. The engineering teams on the surface prepared sealing materials suited for underwater emergency work. Divers carried those materials down to the hull and sealed the leaks with plugs, epoxy cement, concrete patches, and blanking plates where needed. The work was not a permanent cure, it was a controlled emergency stopgap designed to halt the visible release and stabilize the site. The emergency triage operation successfully contained the immediate environmental disaster. The lagoon water slowly cleared, and the acute phase of the crisis officially ended. However, the salvage engineers understood the stark reality presented by the physical evidence they had just examined. The patches created the window needed for a larger response. The underwater concrete could temporarily stop the leaks, but it could not stop the ongoing galvanic decay of the surrounding hull plates. The corrosion problem remained. The salvage force analyzed the containment structure and reached the only durable conclusion. Exterior patching had bought a critical window, but the wreck now required a major extraction campaign. At the lagoon's full depth, the environment imposed severe endurance limits and brutal decompression penalties. The operation became viable because divers could work from the exposed bottom plating rather than descend into the buried superstructure. That geometry removed roughly 40 vertical feet of punishing water column pressure from the main worksite. That 40-foot advantage shaped both physiology and project economics. Near 90 feet, the teams could rely mainly on standard surface-supplied air and complete longer industrial work cycles with reduced but still real decompression penalties. That geometry made the extraction repeatable enough to attempt at scale. While the depth mathematics were highly favorable, the sheer scale of the flat steel expanse introduced a severe subsea navigation problem. The exposed bottom plate was over 500 feet long and heavily encrusted with decades of dense marine growth. To extract the oil, the divers needed to access the primary cargo tanks hidden entirely beneath the steel skin. That trapped buoyancy made the target unforgiving. To pump each tank dry, the engineers had to reach the highest structural point of that compartment. The divers faced a massive, featureless plane of heavily corroded steel. There were no exterior hatches, access panels, or visual landmarks on the smooth bottom plating to indicate the complex internal architecture. Drilling into the wrong section of the hull meant hitting empty structural voids, heavy intersecting steel bulkheads, or deep web framing. A blind penetration at the wrong coordinate could miss the trapped payload or drive into structural framing. The salvage force had to mathematically project the invisible interior onto the exterior skin. To solve this absolute navigation requirement, the engineering team relied on the original 1944 naval construction blueprints. They painstakingly translated the complex internal dimensions of the specific cargo tanks into a massive, two-dimensional surface map. On the deck of the salvage support ships, the crew fabricated an extensive physical template. They constructed a massive measurement grid utilizing heavy industrial wire and precisely measured cable intersections. The diving teams carefully deployed this rigid wire matrix down through the water column and dragged it across the flat steel plane of the inverted hull. To permanently secure the navigation template against the constant surge of oceanic currents, The divers locked the wire intersections down using hundreds of powerful industrial magnets. The heavy magnets bit aggressively into the corroded steel plate, establishing a perfectly scaled physical coordinate system directly over the hidden cargo holds. Using the blueprints and wire pathways, the divers could move methodically across the mapped hull. The grid brought each team to the marked high point of a target cargo space. The invisible internal geometry was officially mapped onto the exterior hull. With the highest cargo points marked on the exterior steel, the crisis shifted from navigation to penetration. The divers were positioned above highly pressurized bunker fuel, separated from it only by deeply corroded metal. The divers were now positioned directly above millions of gallons of highly pressurized bunker fuel, separated only by deeply corroded metal. The fundamental engineering crisis immediately shifted from navigation to penetration. The salvage forces had to open the hull only through a controlled, sealed path. However, standard marine cutting torches or heavy mechanical saws were strictly forbidden. Slicing an open access hole through the half-inch steel plate would immediately expose the pressurized cargo to the ocean environment. The heavily buoyant heavy oil would violently evacuate the tank and surge directly into the water column, creating the exact environmental disaster the salvage force was deployed to prevent. To cut through the hull without opening the cargo to the lagoon, the engineers relied on a sealed industrial process known as closed-loop hot tapping. At each marked point, divers installed a pressure-tight fitting and valve assembly. Specialized equipment then allowed the salvage team to create a controlled penetration through the hull while keeping the surrounding water and the trapped oil separated. The principle was simple. The underwater execution at roughly 90 feet demanded expert planning, Navy diving procedures, and constant supervision. Once the sealed system was in place, the cutter opened the tank through the valve assembly and was withdrawn inside the closed housing. The valve was then secured, leaving a controlled access point for pumping. The result was a controlled pumping point rather than an open breach in the hull. The next hurdle was moving the highly viscous fluid through a closed-loop extraction manifold built for extreme resistance. Heavy-duty, electrically driven submersible pumps were lowered directly onto the hull. The dive teams bolted the heavy machinery to the flat steel and securely attached reinforced industrial hoses from the pumps directly into the 4-inch gate valves. When the valves were carefully reopened, the submersible pumps activated, violently forcing the heavy oil directly out of the deep cargo holds. The heavy fluid was pushed laterally across the vast plane of the inverted hull and fed into a primary collection manifold securely mounted on the bilge keel of the dying ship. From this central accumulation point, massive booster pumps engaged. These secondary systems supplied the pressure needed to move the cold, dense liquid through the vertical lift. The boosters forced the heavy black oil rapidly up through thick vertical hoses. The primary cargo successfully cleared the water column and aggressively poured into the massive storage tanks of the surface support barge waiting safely above. The hardware worked flawlessly on a single tap, but the operation now had to be replicated across dozens of tanks under extreme psychological pressure. The extraction phase now became a test of repetition under zero-tolerance conditions. The salvage teams had to carry that sealed penetration sequence across the hull, adapting each tap to steel that could be sound in one section and badly degraded in the next. There was no room for human error, mechanical fatigue, or momentary lapse. A stripped bolt, a failed underwater weld, or an improperly seated brass gate valve could break the closed system at the worst possible point. Under this immense compounding pressure, the naval dive teams entered a grueling cycle of relentless industrial labor. The work required extreme physical endurance and rigid, uncompromising discipline. Over the span of the subsea campaign, the engineering forces successfully executed more than 200 dives. They lived and worked on the steel plane of the inverted hull, accumulating nearly 11,000 minutes of highly focused bottom time. The divers operated pneumatic tools, managed extraction hoses, and stabilized heavy drilling gear against the resistance of the water column. The physical fatigue was cumulative, but the operational tempo could not slow down. Every movement, every turn of a wrench, and every visual inspection was calculated to maintain the absolute integrity of the dying steel envelope beneath their heavy boots. This physical execution was constrained by a non-negotiable ethical boundary. The wreck was a protected military casualty, with the forward sections containing the remains of American sailors lost in 1944. To honor that boundary, the salvage force worked primarily from the exterior skin and controlled cargo spaces. Entry into manned compartments was forbidden, unlike standard commercial salvage, which might cut away large sections of hull to reach internal holds. The Navy accepted a major handicap. Exterior taps remained the primary method, and any controlled internal access was limited to cargo spaces or previously emptied areas. Significant portions of the internal wreckage remained undisturbed. The mission's success depended on holding both requirements at once: remove the toxic cargo and leave restricted zones undisturbed. Through hundreds of descents and thousands of minutes of controlled execution, the crews tapped the accessible, pumpable cargo spaces without significant spill. The final brass gate valve was sealed against the flat steel plate. The extraction hoses were hauled upward toward the sunlight, and the human phase of the salvage ended with only the final calculus of the cargo itself remaining. Nearly 2 million gallons of heavy naval fuel oil and diesel now sat in the internal containment holds of a commercial surface barge above the wreck. The subsea extraction phase was officially complete, but the physical presence of the captured cargo remained a profound operational problem. This immense volume of recovered fluid was inherently lethal to any marine environment, yet it retained a highly significant industrial value. The massive military salvage deployment required immense financial resources, with reported costs varying across later summaries. Whether counted narrowly as the offloading operation or broadly as the full response, the mission was a multi-million-dollar intervention. Deploying heavy engineering ships, maintaining a continuous subsea presence, and transporting specialized diving personnel across the Pacific Ocean carried severe economic weight. The recovered bunker fuel also offered a way to offset that expense. Because the closed subsea loop kept the tanks from open exposure to seawater, the oil was not heavily contaminated and remained a viable combustible hydrocarbon. Because the fuel still had commercial value, the Navy sent the payload to an international processing hub. Loaded deep under the recovered cargo, the barge left the atoll under tow for Singapore. This long-distance ocean tow represented the physical conclusion of the environmental crisis. As the heavy barge slowly disappeared over the horizon, the toxic mass that had loomed over the local subsistence fishing grounds for decades was permanently eliminated from the geographic equation. Upon arriving safely in the port of Singapore, the massive volume of heavy oil was successfully transferred from the barge into commercial holding facilities. In Singapore, the recovered bunker fuel was sold into the commercial industrial market for large-scale recycling, power plant fuel, or refinery feedstock. Revenue from the sale was applied against the subsea extraction campaign, offsetting a significant portion of the reported $11 million operational cost. Back in the silent depths of the remote lagoon, the massive steel wreckage assumed its final permanent state. Nearly all accessible, pumpable oil had been removed, though small inaccessible residues may remain. The surrounding lagoon no longer carried the same catastrophic oil risk, and the wreck remained below in its post-extraction state.